Hey class, I'm sorry I forgot to go over knowledge check number 10 this week in class, so we're going to go over that solution real quick in a video here. So the first thing, we were given an h of s with some omega of s, and we need to do the z-domain transfer function using this prototype, and we are going to use pole zero matching to find k and alpha. First thing we want to do is sketch the Bode plot of the solution. So we're going to start off by putting h of s into the standard form. H of s is going to be equal to, we want to factor out a 2 from the denominator, and that's going to give us the 5/2 out front times 1 divided by s divided by 2 plus 1. We then want to find the decibel gain of the constant. So this is 20 log of 5/2, which is going to be equal to, we can grab a calculator and make sure you're doing this in logarithm, not natural log. So 20 times the log base 10 of 5/2. There were some assignments where people are still doing this with the natural log, and if you did that, the output would be 18. If you got 18, you're doing the natural log. You want to make sure to do log base 10. So that comes out to be 7.9588, or approximately equal to 8 decibels. All right, so now we can do the Bode plot based on these two things. And if we come over here, we can do a line at 8 decibels. That's the constant. And then we're going to go and at the value of omega is equal to 2, we're going to drop down at 20 dBs per decade. So if we want to come and get the straight line approximation, let's do that in orange. We can add the asymptotes together. Oh, I forgot to put the 3 dB correction point. This is right here, 3 dB correction point. And so now we can come and we can do the straight line approximation for the Bode plot. It's going to come over here until we get to the value of 2. And at the value of 2, we're going to go down at 20 dBs per decade. Now, we can go ahead and add in, if we want, that we are going to have the 3 dB correction point. So that's 8 minus 3 gives us a 5 dB. And now if we want to do the smooth line approximation, we can come and we can pass through that 3 dB point and over to the line. And so we can get our straight line approximation. 3 dB correction point puts it at 5 dBs, and then our smooth line approximation through there. All right, so that's what we need to do. So we can look at this and we can say now, this is a low pass filter. This is going to be at 8 decibels. We also know that we have a constant gain in linear terms of 5/2. So now let's start going through and doing the pole zero matching. So we want to do part B, and we want to find the alpha in z minus alpha. In order to do this, we want to match up the poles. So we can look at this original location, and we can say that there are poles at s is equal to -2. So that's how we want to solve this denominator, is to get the pole at -2. Well, to do that, we're going to use this value. So we're going to put -2 into z. That will cause this to be a pole in the denominator. So we get z is going to be equal to e to the 2 pi. And here's the S is equal to -2. And so we're going to do a -2 divided by omega S. Omega S is equal to 18.12. So now again, if we bring up MATLAB or your calculator, whatever you have to do this, we're going to see that all we need to do is do exponent of 2 times pi times -2 divided by 18.12, and that's going to give us 0.4998. 0.4998. So that is going to be approximately 0.5. Now we're going to find part C. For part C, we're going to look at the constant value. Now this we want to find in the passband gain sector. Because we're at a low pass filter, we can find it at DC. If this was a high pass filter, you'd want to find it at the high pass gain value. So you need to look at your Bode plot and correlate where the gain is at with the given frequency in which you want the gain to occur. So for part C, we're going to say the gain at DC. Let me make this DC. Due to low pass filter. And we can go all the way back and just plug that into this original H of S if we want to, because when we do this, we want to get the linear gain, not the decibel gain. So we're going to say the absolute value of H of 0 is going to be equal to, and then we plug S of 0 into here. That is going to give us the absolute value of 5 divided by 0 plus 2, which is going to be 2.5. So that's what we want our gain to come out to be. So how do we set this up to equal 2.5? Well, we know that Z is going to be 1 at DC, because if we plug it in here again, so for Z of DC, that's going to be equal to e to the 2 pi times 0 divided by omega S, and so that's going to be equal to 1. And so what we want to do now is say that we want 2.5 is going to be equal to K divided by Z minus the alpha value that we found in this last part, which is 0.5. And we know that for this one, we're going to say Z is equal to 1. And so this is going to be equal to K divided by 1 minus 0.5, which is going to be equal to K divided by 0.5. Therefore, K is equal to 5. Let me make 0.5. I'm sorry. I messed something up here. Hold on just a second. I'm sorry about this. 2.5, 5 halves, divided by, not multiplied by. I'm sorry. Let me erase this last step. When you solve that out and you do it correctly, this comes out to be 1.25. So that's what we want the answer to be there. And we have that alpha is equal to 0.5 here. And so now, if we want to put this together to form the overall H of S solution, let me minimize some things on this side so I can free up just a little bit of space. We can see that given all this, what we are going to get as our final solution is that H of Z is going to be equal to 1.25 divided by Z minus 0.5. So this is our overall answer for plugging in HFS.